Hi, my name is Andrew, and I'm joined by Andrew, and our project is on story generation informed by character intentions. Now you might be wondering, with recent advances in language models such as GPT-2 and GPT-3, why can't I generate Lord of the Rings yet? That's a good question. These models fundamentally have some memory issues. GPT-2 is modeling a probability distribution for the next token given previous tokens. Basically, that means that these models are great at grammar and very short-term text cohesion, but we can't squeeze a book into the right-hand side, and so we inevitably run into issues with logical coherences and even remembering a character's name that hasn't appeared for a while. For instance, we give it a prompt about scientists discovering unicorns speaking English, and it starts out good, talking about a study, but then forgets the topic and talks about nanomaterials. We also get stuck into these repetitive loops because the model finds some pattern and either recognizes that it should repeat the pattern, or can't think of anything better to spit back. But that's not how humans look at stories. We want progress towards goals, we want characters with motivations and a logical world with cause and effect. And readers are creating this coherent world model out of the relationships between events and goals, formally defined below, and these should persist no matter how much text goes between them. For instance, if I call takeout and then two unrelated paragraphs happen, readers would still expect, even anticipate, the takeout to arrive sometime, a causal consequence. By the way that it's modeled, GPT-2 has a really hard time keeping track of information like that. And so then we get into building this model with common sense reasoning. Atomic is a dataset of common sense relationships, and COMET is a language model trained to generate likely common sense relationships from an input sentence. In total, we're going to look at 6 of the common sense relationships listed in the bottom left. We can tie together sentences with these relationships. I'll give you an example. A want is a goal initiation, and X intent is a character intention. Let's say we have a sentence, S1, A impresses B, and extrapolate with COMET that B wants to support A. When we arrive at S2, B votes for A, we extrapolate that B wants to support A. Connecting these two, we then have a narrative coherence. In our phase 1 system, we have code to take in any given text, use the COMET model to derive common sense information about the event, and note with the help of a language model to what extent the event is consistent with the information we've seen so far. The user can then choose to either try with a different candidate or add the text to our story so far and update our information about the overall state.
So here you can see COMET and Atomic makes predictions on how car 2 feels about being robbed by car 1 and what they may want to do in response. Here, COMET and Atomic suggests a possible motivation for car 2 to hit car 1 with a baseball bat was to get revenge, and that was an angry thing to do. We can use code to note that it would make sense for this event to follow from car 1 stealing from car 2 in the previous sentence. Now we update the overall state to note how car 1 may react, and note that the consequences of car 1 stealing from car 2 have in part been accounted for.
The biggest gap between our phase 1 system and our desired product is the lack of actual text generation itself. Human text generation doesn't require automated human common sense. And we'll solve this by fine-tuning the GPT-NEO model on the ROC story dataset. Our fine-tuning was pretty standard. We used the ROC Stories 2016 dataset to fine-tune our model. This dataset is a collection of 45,496 stories, each story being 5 sentences long. Our data preparation is comprised of using named entity recognition to replace character names with character 1, character 2, etc., although most of the stories were 2 characters at most. We also add an end of text token at the end of each sentence and then tokenize. Finally, we pack the sentence tensors to reduce memory usage, which helped keep the collab from crashing. We trained the dataset and found that the model at 3 epochs was the best balance of story specificity and not overfitting. And here is our final program flow. Let's walk through both of our user flows. One choice is to have a user input sentence that is passed through COMET atomic, and you can choose to accept or reject it based on the number of intentions that it fulfills. If accepted, we add it to the story, remove the intentions it fulfills, and add intentions that it introduces. If rejected, we go back to the inputs. Alternatively, we can choose to use our fine-tuned GPT-NEO model to generate several candidate next sentences, and the one that matches the most intentions is added to the story. In the case that none of the candidates fulfill any intentions, we start over. Our dual input approach lets a user step in when the model is going haywire or stuck in a rut, while also allowing them to continue using the automated language model when things are going smoothly. And here's a story generated by the language generation model when compared to a story generated by the algorithm that we use to select for text based on the character intentions model. Observe that, for the vanilla model, there isn't a through line, as the crush is forgotten about by the text and characters go to sleep despite having just woken up or already having gone to sleep elsewhere. Meanwhile, for the intentions architecture, every sentence is a response to the previous sentence, such as going to a beach after deciding to go to the beach. For example, intention model decided that it would make more sense for characters who have a crush to go on a date than to be excited about a toy or to be a good boy. This is our model working at its best, prioritizing the sentences that have the greatest through line with our lingering character intentions. When we first tried to use our model without a prompt, we noted that the generated text would not generate text with terms such as character 1 or character 2, though adding those terms to the prompt solved this issue. We also observed that certain terms would pop up too frequently for certain prompts, which limited text randomness until we started filtering out those words. Another failure case we observed was repetition. The intentions that would allow a sentence would also be the same intentions allowed by the sentence, which could allow and encourage repetition in a circular fashion. And thank you for listening.